Compactness. So a topological space is called compact if for every its open cover there exists a finite subcover. So I'm going to give you an example. So let us consider the interval from 0 to 1. So we are going to have like a real line and the interval from 0 to 1. So this is going to be my x, right? This is going to be my x, the interval from 0 to 1. Now let me introduce some infinite open cover, even uncountable open cover, right? So for every x in this interval, I'm going to consider the interval from x to minus 1/3 to x plus 1/3, right? So it is going to be covered by uncountably many um, of these intervals of length 2/3, right? So like, I don't know, this one, and so on. So this one. So there are uncountably many um, open intervals of length 2/3, and together they cover our interval from 0 to 1, right? So their union contains our open interval. And the question is it possible to find finite subcover? And the answer is yes, of course it is possible to find finite subcover. So this is what we're going to do. So the first interval, the first kind of um, element of our finite subcover is the interval from negative 1/3 to 1/3. The second is from 1/3 to 2/3. The third is from 1/3 to 1, and the fourth is from 2/3 to 1 and 1/3. Right? So overall, we have, out of infinitely many intervals, open intervals, we only selected 4 that together still cover the whole x, right? So from negative 1/3 to 1/3, from um, 0 to 2/3, from 1/3 to 1, and from 2/3 to 4/3. So together, these 4 intervals, they contain my closed interval from 0 to 1. The whole real line is not compact in the standard topology because the whole real line, you can um, cover it by, say, all the intervals of the form n minus 1 to n plus 1, where n is any integer. So together they, of course, cover the whole real line, but any finitely many of them do not, because, well, the length of every one of them is 2, and the total length of any finitely many is still finite, so they cannot cover the, the whole real line. Well, and you know from real analysis that a subset of Rn is compact if and only if it is closed and bound. Very nice theorem, so it gives a complete description of compact sets for Rn. Right, so if you have an abstract topological space, well, it doesn't work anymore, but so we have our definition via open covers and subcovers. Now, compactness is a topological property, but unlike the fixed point property, it is preserved just by continuous functions. So the continuous image of a compact space is compact. So F does not even have to be a homeomorphism here. So let me prove this theorem. So the proof is actually kind of simple, right? So the image is compact. I mean, not the whole Y is compact, but just the image. Well, how do we know? So let us take f of x, right? So and suppose that there is an open cover of f of x, right? So f of x is covered. So here I do not write equals because I write a subset because we have a bigger space y, and every open set in f of x it comes from some open set in Y, right? So it is the intersection of an open set in Y and f of x. So the union over all alpha of some u alpha, right? Well, but then, so let us consider, um, let us apply the inverse image, right? So let us take the union over all alpha of f inverse of u alpha. Now, every one of them is an open set. On the other hand, since all the u alpha, they cover the image of f, it means that their pre-images cover the entire x. So this is going to be the entire x, right? So which means there exists an open, a finite subcover in that open subcover, right? So it means that there exists just some finitely many alpha 1, alpha 2, and so on, alpha n, such that f inverse of u alpha 1 union and so on up to f inverse of u alpha n already covers x. But then going back to the image, we see that f of u alpha 1, um, sorry, just u alpha 1, image with u, sorry, the union with u alpha 2 and so on, u alpha n, they are going to cover f of x. So which means f of x is common.